In the last video, we went over where E comes from and how it was calculated. We looked at the binomial theorem and how it was used to calculate E. Now, one of the last things I showed you is what happens when we raise E to the power of x. Now, hopefully this section in red here looks a little bit familiar to you. We have the binomial expansion that creates E. So as n goes to infinity, 1 plus 1 over n to the nth power creates this nice little pattern here, 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. And that goes on forever like that. And this infinite sum of these things adds up to E. Now in the blue here, we have the result of expanding this binomial, 1 plus 1 over n to the n times theta times I. So it's a little bit of a different power here. So this is actually the same as raising E to the theta times I. And this is what it looks like in binomial form right here. This should look very similar to the example in the last video where I showed you how to raise E to the power of x and what that result looked like. In this instance, it just sort of looks like the power of theta times I gets multiplied into what we had when we calculated E here. So adding this new power of theta times I, it really looks like it just multiplies theta times I here, theta times I squared here, theta times I to the third here, and that's what's happening. And you get a very similar pattern to what we got with E. It looks very, very similar. And you know, if you look at the last video on what happened when we raised E to the power of x, that would help clarify things if you haven't seen that. But anyway, this is the expansion we get when we do the math here and expand this. And again, this is equal to E to the power of theta times I. Now, don't be confused by theta here. Theta is just some random unknown variable. And what this all adds up to be depends on what value we select for theta. You know, most of you who are watching this, you probably know that if we put pi here, you know, e to the pi I, this should all add up to -1. But there's actually an infinite number of variables that we can put in here. And in the first part of this video, we're gonna examine what happens when we choose different values for theta. One of my favorite YouTube channels is 3 Blue 1 Brown, and they have excellent math videos that illustrate and explain math concepts very well. This channel has their own explanation of Euler's identity, which is e to the pi I, and what we're talking about basically here. I have a link to their video in the description. I recommend you watch it. It's really informative. Anyways, I'd like to show you a few screenshots from this to quickly go over what happens as you change the value of theta. Here we have the same binomial expansion that we had on the previous slide. 1 plus theta times I plus theta times I squared over 2 factorial, theta times I to the third over 3 factorial, theta times I to the fourth over 4 factorial, and going on into infinity. And what they're illustrating to you here is what happens inside of here when theta has different values. And we go through this a little bit. We're going to start with 1, and here we have the complex plane. So we're just going to move 1 in the complex plane, which is to the right. So this 1 maps to moving 1 to the right. Now theta is 1, so we're going to just sort of ignore theta in all of these. It makes it nice and easy because it's just, you know, 1 times I, you know. So let's ignore that. So here it's moving plus I. So that in a complex plane moves it up I. So we're here. Now we have I to the squared, I squared over 2. So that's going to be moving -1/2 basically, because the I squared turns -1 and over 2, so -1/2. And each of these little arrows here, you start to lose track of them, are the successive terms after that. And they get smaller and smaller because these factorials sort of win over what's on top, and you end up dividing by bigger numbers than you have here. And what it does, interesting enough, is for every value of theta, it will actually put you on a unit circle here, and we're going to see that as we go from slide to slide and use different values of theta. So just to recap, for every value of theta that we pick and plug into this expression, we're going to get an answer that falls on the unit circle in the complex plane. So that means, aside from -1 and 1, every section of this unit circle is a complex number. So I think if we plug in 1 as theta, we get something like 0.54 plus 0.84i. So again, it's a complex number, and so are the rest of these points. So that's what we should be expecting as an answer. But obviously, you know, some of the nice values are going to be like 1, -1, I, and -I. But everything else is going to be some decimal with a real component and an imaginary component. You know, not many nice numbers on here. Now, if you actually watch their video, which again I recommend you do, the illustration is very nice. It slides nicely around. I don't have anywhere near that production quality in my videos. But here is a screenshot where theta is pi, essentially. And you know, your first term is still a 1, and then you have pi I. You're moving up pi I, and then pi squared I. Pi I squared over 2. That gets you going in a negative direction, just like we did before, and it lands you here. So, and then this guy moves you down, and they all sort of conspire to, again, put you back on this unit circle. So, you know, he slides it very smoothly right around this unit circle as theta goes from 0 to pi. And as he increases theta, it continues to go around the circle. And he does mention that that's not a very obvious thing from looking at this equation. So we essentially have to dive deeper and to try to figure out, why does this go in a circle? Like, what is making this happen? And in the next section here, we're gonna take a look at another video from the YouTube channel Mathologer, and he has very, very good illustrations and very good descriptions on why it goes around in a circle. So here's a screenshot from the Mathologer YouTube channel on a video about e to the pi I. I have a link in the description, and this probably has the best explanation, hands down, of why e to the pi moves in a circular fashion around the unit circle. I've stopped on this slide because I think this reformatting of the binomial is key to understanding the entire thing. You know, this is how I look at it. So, you know, once you have it like this, it becomes a lot clearer, especially if you have some understanding of complex numbers. So, basically, this binomial, which was 1 plus 1 over n to the n times pi I, has been rewritten as a complex number, 1 plus some number I to some power. And this is very important, especially if you remember the first video about what we talked about, what happens when we raise a complex number to a power. And I'm going to go over that again a little bit right now. So first, let's again revisit what e to the theta I looks like, which is this binomial, 1 plus 1 over n to the n times theta times I. Now, if you remember from our first video, we saw that the effect of an additional variable in the power here, it had the same result as being in the rate. So if we had, say, e to the x, it would be like making this an x. So again, if you don't know what I'm talking about, you might want to review the end of the first video there. But that's what lets us sort of rewrite this as something like this. Clear that up and clean it up. So here we have now 1 plus theta I over n to the nth power. And we could just do a little bit of a reformatting there and just put 1 plus theta over n times I. It's just really the same thing. It's just sort of, now it's written like a complex number. And again, all of these are the same thing as e to the theta I. It has the exact same result for all of these. So these are all equivalent to one another. So now if we look at the case where n goes up really, really high, we're left with a complex number with a very large real part, or at least compared to the imaginary part, we have 1 as the real part, and this microscopic little 1/10,000th of an I, which is very small. And of course, it's raised to the 10,000th power. But the point is that as n goes up, this gets smaller and smaller and smaller. So this, as n goes up to infinity, this approaches just 1. And you'll have some 1 plus, really, some infinitesimal, 1 over infinity-ish I. Again, to the infinite power, right? Because as n is going to infinity, you're going to end up with something like this, where this is just some little infinitesimal amount. So this whole thing inside here approaches 1 as n gets bigger, and that's going to become important. So let's do a quick refresher here. We have a complex plane with the i's in the y-axis and the real numbers in the x-axis. And let's say we had some complex number that was maybe, let's say, right about here on the complex plane. Some real portion and some imaginary portion. And let's say the distance between the origin and there was 2. Now, when we squared this complex number, whatever it may be, a plus bi, and we squared it, a couple of things happen. The distance here, that's in green, which is right now it's 2, that squares. Another interesting thing that happens with complex numbers is this angle that is made when you draw this line. That just goes up another 30 degrees. So it goes up the same value for the angle that already was in here, and it just goes up another, say, 30. If this was to the third power, you would have, again, we starting off with this complex number that with a distance of 2, an angle of 30 degrees. Well, this distance is going to be raised to the third power, and you're going to end up with an 8. And this 30-degree angle will be repeated 3 times, and that's the angle that your complex number is going to be at. Now, why is this important? Well, I'm going to show you some more slides from the Mathologer video to hopefully explain this a little bit better. So the big thing to look at is where your complex number is compared to the unit circle. Now, if it's outside the unit circle, this distance from the origin here is greater than 1, which means when you square it, cube it to the 4th power, and so on, it's just going to get bigger. It's also going to rotate, which we talked about, whatever angle this is, right? You're going to raise it to some power, and if you raise it to the 5th power, it's going to go 5 of whatever this is. So let's say this was 20, it would go 40, 60, 80, 100, and so on. But again, this is longer than 1. So it's going to get bigger and bigger and bigger and spiral away from the center. Okay, so what about if your complex number has a distance of less than 1 when you're comparing it to where it is on the complex plane to the origin? So let's say maybe this is like 0.8, right? This distance from here to here. Well, as you square it, cube it to the 4th power to the 5th power, that number would get smaller. And again, the angle rotates. Again, it doesn't matter, what this value is or where it is on the complex plane. But whatever angle you're starting with here, it will just repeat with every power that you raise it to. But again, the big thing to take away from this is inside the unit circle, less than 1, you get closer and closer to the origin. So it sort of like spirals in here. And now finally, if you're on the unit circle, where this has a value of 1, this distance from the origin has a value of 1, well, guess what? It's really like you're squaring, cubing to the 4th power. You're raising 1 to those powers, which means it's just going to be 1 all the way around. The angle is going to be repeated just as it is. So if this is a 20 degree, you get 20, 40, 60, 80, 100. So, each power that you raise it will again rotate it the same increment of degrees that this is. So again, the important thing to realize here is if it's on the unit circle, it will rotate in a circle when you raise that to a power. Now, why is that important? So let's return back to how we rewrote e to the theta I as in a more friendly complex form, right? We just like is shown in the Mathologer video, we could write it as basically a complex number raised to a power. So we have it here as 1 plus theta over n to the times I to the nth power. So if theta equals 1, right, just a nice easy number. Again, we get to choose whatever we want theta to be. So just for now, we're going to choose 1 because it makes it nice and simple looking. And let's make n some crazy high number like 10,000. So now we have 1 plus 1/10,000th I to the 10,000th power. Now the thing to take note of is that this is a very small imaginary portion. It's very close to 1. Right? It's very close to that unit circle where if we raise that to a power, it's always going to be on that unit circle. And in fact, as we have n go to infinity here, we have some infinitesimal portion of it imaginary, and we have 1 in the real part of the number. And this is basically approaches 1. This as n gets bigger, this approaches 1. So it's basically on the unit circle. And we're raising that complex number to a power, and it's going to stay on that unit circle. Now, even if you don't like dealing with infinitesimals and infinities, you could pick a sufficiently large value for n here, and you're going to be able to approximate this extremely close. This is not going to move much away from the unit circle unless you have very large values of theta. This is essentially going to stay on the unit circle, and it's going to approximate it extremely close. And add enough zeros, and you will no longer have to care about the difference between what this results in and the unit circle. The Mathologer video has some really good illustrations here. They just used 100, and you see how close you get to the unit circle with just 100. And again, like I said, you add more zeros to this, and you make n a bigger number, and it's going to be indistinguishable from the unit circle. And this is a pretty good illustration of that right here. So the last thing I want to go over before this video ends is what happens with the angle with this really small complex number. Here I have 1 plus 1/1,000,000th I. It's very tiny. As you can see, this is the y value here, or the complex value, is 1 times 10 to the negative 6th I. And this is right here, this blue line is our unit circle, which zoomed in so close it looks like a vertical line, not a circle. But this is creating a very, very small angle. It's a very small angle in degrees here. If we zoom out, we could see exactly how small it looks like a horizontal line, but it's not. It is in fact a very tiny angle. And since we are using n as 1 million, so in Euler's formula there, we have 1 plus 1 over 1,000,000 I to the 1/1,000,000th power. What this little tiny angle is just going to be repeated 1,000,000 times. So again, it will be moving in even increments. So this is going to come into play in the next video, where we're trying to find out, well, why pi? Why does pi make it rotate around? And again, it's just important to remember that this little tiny angle that forms here is going to be repeated. If we used 1/1,000,000th I, it's going to be repeated 1,000,000 times. And wherever that ends up is where you're going to be on a unit circle. And just before I go, I just want to go over one more quick thing here that might drive the point home. Let's take I to the 1 over n as n goes to infinity. So any power of I is, of course, going to be on that unit circle, right? Because I is really just a form of radical negative 1. It's always going to have, any power of I is always going to have a distance of 1 on that from that origin. So let's raise this to some really high power. Really high value of n, maybe not infinity, but we're going to get something like 0.99 plus 1/100,000th I. And this actually looks very similar. The higher we go with n, the more this is going to approach 1. And that's very similar to what we got with either theta I here. As if we say theta equals 1 here, and we increase this size of this n value to 100,000, this also gets very close to 1. And as n goes to infinity, it gets closer and closer. And the same thing's going to happen with this. These things are approaching the same value. Granted, this is from outside of the unit circle, so it's slightly different. But if we can see how these are very, very close to one another, we can look at what happens when we raise I to the 1 over n to the nth power, just as what we're doing with Euler's identity here. Well, that's some very easy algebra. This equates to I to the n over n, which is just I to the 1. And you're just going to be still on that unit circle when you're at I to the 1, because it's just 1 in the y-axis. So, if we were to do this, and put 100,000 up here, you're going to get exactly the same answer for this that you do with this, more or less. Or rather, I shouldn't say the exact same answer. It's going to be slightly different, but it's all going to be on the unit circle. And you can sort of see how this would rotate around the unit circle pretty easily, I hope, because any power of I is just going to rotate around the unit circle when you raise that to a power. It's always going to be an I. It's never going to turn into a 2i or a 3i or anything like that. It's always going to go around that unit circle. And if you could sort of see how this Euler's identity here gets you to the exact same place, I think you have a good concept of understanding as to why it rotates. All right. On the next video, we're going to try to look at why pi gets you 1/2 a rotation. And that's going to be a bit of geometry, but hopefully I can make that clear for you